Metal frames have long been a foundation of modern construction, manufacturing, and design, offering a unique combination of strength, durability, and adaptability. When used as structural elements, metal frames provide a reliable skeleton that supports loads, resists environmental stresses, and enables wide-open interior spaces that would be difficult or impossible to achieve with other materials. The nature of metals, principally steel and aluminum in frame applications, gives these structures high tensile strength and predictable behavior under load, allowing engineers to design for both efficiency and safety. The uniformity of manufactured metal sections, whether hot-rolled beams, cold-formed sections, or extruded profiles, simplifies calculations and quality control, enabling repeatable production and predictable performance across varied projects. One of the key advantages of metal frames is their versatility. Steel frames, for example, can be fabricated into a vast array of shapes and sizes, from slender sections used in architectural detailing to massive girders that span long distances. Aluminum, though less strong than steel by weight, offers a highly favorable strength-to-weight ratio and exceptional resistance to corrosion, making it ideal for applications where weight savings are critical, such as in transportation and certain facade systems. Metals can be joined using welding, bolting, riveting, or modern adhesive bonding techniques, each method having its own advantages in terms of speed, permanence, and field repairability. Prefabrication is a common practice with metal frames. Components can be manufactured in controlled environments and then assembled on-site, reducing construction time, improving quality, and minimizing on-site labor and waste. Durability is another significant feature of metal-framed systems. When properly designed and protected, metal frames can resist the effects of weathering, pests, and fire better than many organic materials. Corrosion protection through galvanizing, painting, powder coating, or the use of corrosion-resistant alloys extends service life even in aggressive environments. Additionally, metal frames can be engineered to meet stringent fire resistance standards. While bare steel loses strength at high temperatures, protective measures such as fireproofing coatings, encasement in fire-resistant materials, or designing for redundancy can ensure structural integrity under fire conditions. In many industrial and commercial applications, the robustness of metal frames yields low maintenance requirements and predictable lifecycle costs, factors that owners and facility managers appreciate when planning long-term operations. From an architectural standpoint, metal frames enable bold aesthetic choices. Slim profiles and long spans permit large glass expanses and open interiors, which are hallmarks of modernist and contemporary architecture. Exposed metal frames can become part of a building's visual identity, highlighting structural honesty, contrast with softer materials like wood or fabric, and providing crisp, clean lines. The ability to fabricate custom metal shapes means architects can pursue expressive geometries, cantilevers, and unusual forms that would be costly or impractical with masonry or timber. Furthermore, metal framing systems integrate well with other building components, allowing for seamless incorporation of curtain walls, cladding systems, and mechanical services. Sustainability considerations are increasingly important in material selection, and metal frames have notable environmental attributes. Steel is among the most recycled materials globally. Modern structural steel often contains a significant proportion of recycled content, and steel elements can be recycled again at the end of a building's life. The long service life and durability of metal frames can translate to reduced resource consumption over time, provided coatings and treatments are chosen with environmental impact in mind. Energy efficiency in buildings with metal frames depends largely on design details. Thermal bridging through metal elements can be mitigated with thermal breaks, insulation strategies, and careful detailing to prevent heat loss and condensation. Advances in profiling, composite panels, and insulated metal panels help combine structural function with thermal performance, making metal-framed buildings competitive in energy-conscious projects. Manufacturing and fabrication technologies have further enhanced the capabilities of metal frames. Computer-aided design and manufacturing allow for precise control over dimensions and tolerances, enabling complex assemblies to fit together with minimal adjustments on site. CNC cutting, laser profiling, and robotic welding produce consistent, high-quality components while reducing human error. Modular construction methods, where complete modules or chambers are assembled off-site and transported for joining, often use metal frames as the internal structure due to their strength and ease of connection. This approach can significantly accelerate project timelines, improve safety by moving labor to controlled factory environments, and reduce on-site disruption. Despite these benefits, metal frames pose certain challenges that must be addressed in design and construction. Thermal conductivity of metals means that unmitigated framing members can create thermal bridges, leading to heat loss, condensation, and possible mold issues in climates with significant temperature differences. Engineers and designers must incorporate thermal breaks, continuous insulation layers, and appropriate detailing around joints and penetrations to maintain building envelope performance. Corrosion is another concern, especially in coastal, industrial, or chemically aggressive environments. Specifying the correct alloy, protective coating, or cathodic protection system is essential to ensure long-term durability. Acoustic performance can also be an issue. Metal frames can transmit sound more readily than heavier materials, requiring additional acoustic insulation, resilient channels, or floating floor assemblies to meet interior comfort standards. Cost considerations for metal frames vary with market conditions, availability of skilled labor, and the scale of the project. While steel prices can fluctuate, the predictability of prefabricated metal components often results in competitive overall project costs, particularly when lifecycle costs and speed of construction are taken into account. Labor productivity gains from factory fabrication and reduced on-site assembly time can offset higher material costs when compared to labor-intensive alternatives. In addition, the relative lightness of metal frames can reduce foundation loads and associated foundation costs. However, highly customized or architecturally complex metal elements can drive fabrication and engineering fees, so early coordination among architects, engineers, and fabricators is important to control costs. Safety and regulatory compliance are integral to metal frame projects. Codes and standards guide the design for load-bearing capacity, wind and seismic performance, fire resistance, and material quality. In seismically active regions, metal framing systems are often favored because of their ductility and ability to dissipate energy without catastrophic failure. Proper detailing of connections and joints, provision for movement and tolerances, and consideration of dynamic loads contribute to resilient structural systems. On construction sites, handling and erection of metal components require cranes, rigging, and trained crews. Adherence to safety protocols protects workers and maintains project schedules. Practical maintenance and inspection routines help ensure the longevity of metal frames. Periodic inspections for signs of corrosion, fatigue, loose connections, and coating degradation allow for timely repairs and prolonged service life. Access routes, anchor points for maintenance personnel, and designs that avoid water traps and debris accumulation minimize deterioration. When deterioration does occur, metal elements are often reparable. Plate replacements, reinforcement, and localized recoating can restore structural capacity without complete replacement in many cases. In summary, metal frames represent a robust, adaptable, and widely used approach to structural and architectural design. Their strengths, durability, high strength-to-weight ratios, prefabrication potential, and aesthetic flexibility make them well-suited to a broad range of applications, from industrial buildings and bridges to sleek contemporary architecture and modular housing. Challenges such as thermal bridging, corrosion, and acoustic performance can be effectively managed through thoughtful design, material selection, and detailing. With continued innovations in materials science, fabrication, and digital design, metal frames will remain central to construction and manufacturing, offering efficient solutions for both practical and creative demands.